Hello students, welcome to lecture 5. Today we will discuss about source rock evaluation. As you know, source rock is a rock from which oil and gas produce or the rocks which generate oil and gas in the subsurface. Okay, source rocks are any rocks in which sufficient organic matter accumulated, preserved, and thermally mature. These are three conditions you can say that a source rock should fulfill for becoming a oil and gas generator rock. Source rocks are mostly commonly fine-grained, such as shales, fine-grained carbonates, mud-carbonate mixture like marl and coal. Based on literature published up to 2012, 65% source rock in the world were shales and 21% were carbonates. These figures were confirmed from industry. And from this last point, you can feel the importance of shales. That the most of the source rock in the world are shales. So you have to first focus on shales as a source rock. Then you can also check other types of source rock as well in your study area. Okay, first question is whether an organic rich rock will become a source rock. Answer is may or may not. Because it is not the quantity of organic matter in a rock that is important, but the type of organic matter and its thermal maturity. These are actually the 2 points that decide about the future of source rock, whether it will generate hydrocarbon or not. So, type of organic matter and its thermal maturity, these are most important parameters that need to be studied. Only quantity of organic matter is not important. Okay, now what are those types of organic matter, or as you can recall from your previous lecture, lecture number 4, we have studied a little about kerogen, how kerogen formed. Um, Actually, this kerogen is formed after diagenesis of organic matter, and it is kerogen which releases petroleum. So we have to look into kerogen types and its thermal maturity. And if we can study it in detail, what type of kerogen in your study area, how much it is matured thermally, then we can decide about the generation of oil and gas. And the figure in the right side, it is taken from your last lecture. And as you can see, after diagenesis, the organic matter actually converted into kerogen, and it is the kerogen which later produce oil and gas at different stages of ketogenesis. So we will see what are the types of kerogen and also look into its thermal maturity. Okay, there are four types of kerogen as you can see in the slide. And last one, which is type 4, it is rare and practically has no ability to generate oil and gas. This type of kerogen is not important for oil and gas generation. And first three types are important and mostly are the focus point in the industry. What type of kerogen actually exists in a particular area. So we will look into detail how these types vary, what are their properties. Okay, here is a table that helps us to understand different types of kerogen and based on the chemistry of kerogen. As you can see at the top, here are weight percent of different elements like carbon, hydrogen, oxygen, nitrogen, sulfur. And next, the ratio of hydrogen carbon and then oxygen carbon in a particular type of kerogen. And then what petroleum type uh, will be generated from these type of organic matter or type of kerogen. Okay, let's see type 1. The origin of or source material for this type is the algae. It's made from algal. And here are different, you can say, weight percent. And if you focus on carbon, here you can see that about 75 weight percent of carbon exists in this type 1. Similarly, in other types, types 2, type 3, type 3, you can see the variation in organic carbon. Similarly, the variation in hydrogen and oxygen. And then in type 3, there is no hydrogen. And in the same way, the ratio between hydrogen and carbon and oxygen and carbon vary as you can observe the values. And at the end, if you focus at this column of petroleum type, you can relate which type of petroleum will be generated by a particular type of kerogen. Just like type 1 can produce oil, type 2 can produce both oil and gas, and type 3 can produce only gas. So these types of, you can say, studies or these parameters, particularly this organic carbon and its ratios with hydrogen and oxygen, help us to identify the type of kerogen in our study area or the sample we have in the laboratory. These uh, studies will help us to decide either our particular shale contain enough kerosene and thermally mature kerosene, and also will help us to identify the type of kerosene, which type of kerosene and what type of petroleum we can expect from that particular shale. So this table is, you can say, important to get a basic idea about chemistry of kerosene, how chemistry vary with the type of kerosene. Okay, in kerosene classification, here are some more parameters that will help us to classify or to identify type of kerosene. Just in first row, paleontology data, and you can read the same description: algal, amorphous, herbaceous, woody, and coally. And then there are particular terminologies for particular type of paleontology. Macerials, these are, you can say, teeny particles or teeny remains of plants. And here are the particular terminology for those: liptinite and vitrinite and then inertinite. And I will show you image in later stages about these different types of biological markers or biological parameters, you can say, which also help us to identify oil and gas. Similarly, evolutionary pathway with type 1 or type 2, these three, you can say, type of paleontology can exist in type 1 and type 2 kerogen. And similarly, in type 2, particularly kerogen, this type of, you can say, paleontology exists. And then in type 3, those are mostly woody, and in type 4, those are mostly coaly. It's also related to coal. So type 4 is not important, as I mentioned earlier, because as at the bottom you can say very little gas, it may not be commercially viable to extract. So these first three, you can say, column where different types of kerogen have been identified in these materials, you can say algal, amorphous, herbaceous, woody, and these are important for knowing the generation of oil and gas. Similarly, the hydrogen carbonate, oxygen carbonate, here are the different ranges that also help us to identify or differentiate between different types of kerosene. Similarly, hydrogen index, there is a relationship, how we can calculate it. I will explain later in later slides. Similarly, source material, what source material for different types of kerosene you can identify from here based on these data sets. And at the end, what type of hydrocarbons will be generated from these type of kerosene. So this is also again an important table just to get a basic idea about type of kerosene and how different parameters with type of kerosene vary. Okay, this diagram actually a little poor resolution for this, but still you can read the trends for different type of kerosene and their images like how algal amorphous look alike. You can observe here. And at the right side, at this corner, this is your shale. You can say sample, or you can say some fossils as well. And here are the microscopic views of those material and how these microscopic views help us to identify different type of kerosene. And in later slides, I will also show you different biological value thermometers as well. And those also help to differentiate the type of kerosene. Okay, here is more, you can say, explained figure in good resolution. In plate 1, then plate 2, plate 3, plate 4, you can observe different kerosene under a microscope. In plate 1, these are amorphous. In plate 2, herbaceous. Then plate 3, woody. And plate 4, coally. And these will actually give you better idea about these different types of kerosene. These were taken with the help of microscope and will also help you to imagine these types of kerosene from paleontological point of view. Okay, now here are the hydrogen or the product that can be produced from those types of kerosene. As you can observe again the previous slide, like algae and these organic precursors actually can produce mostly liquids hydrocarbon you can say. Similarly, other marine algae, pollen, spores, leaf, waxes, fossilizine, these actually fall in type 2 and can produce liquids, oil you can say. And similarly, terrestrial derived woody materials, these mostly fall in type 3 and they can produce gas. And this is also work done by Waplus in 1985 to differentiate different organic precursors and to relate these precursors with different type of kerosene and then to different type of hydrocarbon products as well. Okay, the other important parameter that actually relate with kerosene type is temperature. As you can see in figure on left side at the middle is the variation in temperature vary from 0 to 250 and here are different lines for a particular temperature 60, 160 and 225. As you move down you can observe your processes are also going to be vary. In first temperature range you are in diagenesis and about this threshold around 60 degrees centigrade, you enter into ketogenesis and also have a kerogen. And then in this temperature range, actually oil generated, and then if the temperature more increases, reach up to 160 or more, then you enter into gas window. Means your source rock will generate gas in this window. Similarly, then later on, metagenesis. And in parallel to this figure, if you also observe this figure on right, it is also called Van Creveld diagram, and it is actually between oxygen carbon and hydrogen carbon ratio. And as you can observe here, these curves differentiate different types of kerogen: type 1, type 2, then type 3. And at the end, also there is one line that I did include here for type 4. And as you can observe here, the different processes like diagenesis will happen both type 1 and type 2 can exist in this zone, and then in ketogenesis mostly all of your three types of kerogen exist here in this process window. And actually this is the area where actually your oil and gas are going to be produced. And also these agree with your hydrogen carbon ratio and oxygen carbon ratio. This is the same data that we observed in previous tables, how we can differentiate between different types of kerogen based on these hydrogen carbon ratio or oxygen carbon ratio. So these data sets from chemical analysis or from geochemistry also helpful to decide about the different types of kerogen. And if we overlay these two diagrams, then we can relate these types of kerogen with temperature window as well. And ultimately at the end, we will have which type of kerogen and where it fall in temperature window or in your oil and gas windows. Okay. Okay, I will suggest that let's go through your chapter 5. There is very detailed discussions about these kerogen types and the figures I discussed just in previous slide. A detailed discussion is given there, and let's read those discussion. And if you feel any difficulty, let's ask question. Let's email me, and hopefully I will answer your question. And there will be a good way to learn about these kerogen types. And similarly, these are very important questions regarding oil and gas generation, like which kerogen type is most suitable for oil generation, which kerogen type is most suitable for gas generation, and which is most suitable for both oil and gas. So let's read the particular part of chapter 5 where the details about kerogen types are given, and then try to answer these questions. Okay. Next, let's suppose if you collect a shale rock or any other type of source rock sample from field or well, how you will proceed. And this process actually will help you to learn a lot about source rock evaluation. Because it is not necessary that every shale is a source rock, or if there is high quantity of organic matter, then again it is not necessary that it will produce oil and gas. So we will see stepwise how we can decide either our particular rock that is deposited in an area will generate hydrocarbon or will not generate hydrocarbon. Okay. First of all, you will go through your literature of your study area, its geology, and also perform some laboratory tests to specify the geological age and geological formations. Sometimes this step one, information for this step one is mostly available. If you talk about Pakistan, Pakistan has already been divided into different basins, and detailed literature study and some basic tests for geological ages have already been performed. You just have to search for relevant literature and to study to specify the different formation which have been approved as a source rock. So that is not a tough task. You can easily perform that task and can specify different formation which are producing oil and gas. And similarly, You next step is to recognize deposition environment. As I mentioned earlier in my last lecture about the importance of depositional environment and how different steps you can follow to recognize the deposition environment, and then at the end why a particular environment is important for source rock deposition and in later stages for reservoir rock as well. So you have to recognize the deposition environment of your source rock as well. And at the end, you will also study the fossils history and geological history of your area, and will assess either that geological history and fossil history support the accumulation or generation of hydrocarbons. There you have to decide. And the other important task or important work to do is the burial history curve. Based on those geological data and deposition environment data, and if you have some temperature information in the subsurface, that mostly available in the literature for a particular area, even in globally, for a particular basin, mostly data is available in literature. So you just have to search out those things and put those things on table, and let's plot those data set and assess about the hydrocarbon presence in your area. So the burial history plots, as I mentioned, is also important. And let's see, here is an example of burial history plot or burial history curves. What data actually we use in it? We use the age of different formations that are deposited or were deposited in your area. And second parameter, you need temperature variation with depth. If you have borehole temperature data, that is good. And if you have only the temperature gradient information about your study area, even from that temperature gradient information, you can um plot these burial history plot as well. So the interpretation of this diagram is not difficult, as you can observe the dark black rectangle or open rectangle here. That is more reddish. That means the temperature is more than 100 degrees centigrade. And if you go back and look into your different processes and different oil and gas windows, you will observe that this temperature actually fall in gas window. Means the source rock that is deposited at this particular depth interval had observed this temperature range. So there is a chance that your source rock that is deposited here will generate oil and gas. And most probably, then we later on specify what the exact temperature of this particular layer, then we can define either it will generate only gas or it will generate both oil and gas. So it's just a game of temperature. If you know the temperature, let's highlight the different oil and gas windows based on temperature information, and then develop these depositional histories of different formation and develop these curves. You can get an initial assessment about the source rock maturity. It is also called thermal maturity. If just like if I observe the temperature here that is less than 50, I can't say that my source rock can produce anything here. But the temperature range more than 100, yes, there is a chance. If we perform some additional tests, we can confirm the generation of oil and gas in this particular layer. So for thermal maturity, you have to draw these types of plots and then put the temperature data on it before going for detailed testing. It will give you an initial assessment. Okay, now what are laboratory analyses of source rock? And these are also known as paleothermometers. Two types, one is chemical and other is biological. And as you can read in this slide, in chemical there are different tests: carbon ratio, electron spin resonance, pyrolysis, gas chromatography, and the tests. Similarly, in biological, Bolan and veterinary. And in this lecture, I will discuss the details about three tests: one from chemical and two from biological. And these, you can say, are frequently used in the industry, so I'm going to discuss. But other tests are also important to reach a final decision about the maturity of source rock. So I will discuss in detail these, and for other tests, you can read the relevant details in your textbook, as well as you can search these tests on Google. You can read about these tests as well. Okay, now first of all, what is pyrolysis? Okay, this text actually was taken from your book, so you can go there and read further details about pyrolysis. And what is pyrolysis? Pyrolysis is the heating of kerogen or source rock, source rock where kerogen exists. Um, the process developed to produce petroleum from oil shales. Today, the pyrolysis of kerogen samples is an important laboratory technique in source rock analysis. Pyrolysis is carried out with a flame ionization detector. Initially, it was necessary to separate the kerogen from the source rock. As I mentioned earlier, there is a source rock which actually contains kerogen. And in first step, you have to separate kerogen from source rock. And nowadays, however, analysis can be carried out on whole rock as well. Depends on your equipment, what type of equipment you have in your laboratory. And the main step is the sample is heated in a stream of helium. And then we observe, after heating the sample and increasing the temperature, and what happened to kerogen. That is actually the main goal, to observe different variations in kerogen and to interpret those variations to conclude about kerogen maturity. Okay, here is a quick idea about what type of equipment these are. Pyrolysis analyzer, you can also say it's a rock eagle or rock eagle 6 model. And what we do actually, we collect the sample and convert it into a rock powder. There is a specific requirement what grain size we should have to achieve. You can look in detail on this website. And then weight that powder and put in this specific setup, and then run this ionization detector. And we also have a software that's actually attached with this equipment, and whatever this equipment observe the variation of kerogen that actually plotted on the computer software. And what plots we get, let's look at another slide. Yeah, it is a typical plot that actually we got from that pyrolysis test. As you can observe, the traditional heating program is shown below and is broken down into three phases. First phase, one, that also we call it isothermal phase. Second is ramp, and then cooling phase. And in different phases, you can observe the different temperature ranges and different timing. And in first phase, samples are heated to 300 degrees centigrade and remain there for 3 minutes. And under these conditions, we actually observe free hydrocarbons, which are actually volat- volatilized and measured as S1. Similarly, in next stage and then in last stage, we observe the different hydrocarbons, those are generated at these stages. Okay, here are details about each stage. And let's read this stage 1 isothermal phase. During this phase, free hydrocarbons that have already been generated in nature prior to pyrolysis but are held within the source rock. They are still in source rock. Those are actually volatilized and measured or volatile. So the hydrocarbons associated with this phase are called S1 and are reported as milligrams of hydrocarbon per gram of rock. This is a typical unit you can say use for this phase. Theoretically, if a source rock sample is thermally immature, no hydrocarbon will be measured during this step. This is a very key point that you have to learn about the thermal maturity, how we decide either our kerogen is thermally mature or immature. And what's the reason? Because the source rock hasn't generated any hydrocarbons yet. But realistically, even a completely immature source rock has a minor S1 peak. Maybe the hydrocarbons are there, but still they are not generated. And then we will further increase the temperature. During this phase 2 or RAM phase, the thermal cracking of kerogen and large molecular weight hydrocarbon within the source rock takes place. As the source rock is forced to thermally mature, now we are going to thermally mature the source rock and we'll see what we get. The hydrocarbons that are generated during this phase are measured are called S2 and are also reported as milligram hydrocarbon per gram. And here actually what we did, we increased the temperature beyond 300 to 550. And at some point, if that particular sample has reached to that temperature, and at that point we can say that okay, it will generate hydrocarbon when it will reach at this temperature. And if it has already been generated hydrocarbon below this temperature, you can say the hydrocarbons are already it has already been generated in that particular type of source rock. Okay, last step is cooling phase. And during last phase two, not only is the source rock being forced to thermally mature in order to generate hydrocarbon, but it also generates CO2 during the thermal decomposition of the kerogen. While the CO2 is actually generated during phase two, it is held in a trap until phase three, where it is released and measured. And mostly CO2 actually measured at this S3 phase, which were actually accumulated in previous step as well. So it is measured in CO2 per gram of rock. So this is the basic interpretation about different types of, you can say, products we obtain after heating the kerogen, and it's all going on in that particular ionization detector that we just have seen in previous slide. And at the end you got a plot of S1, S2, S3, and based on those plots you decide about the maturity of kerogen. Okay, let's observe another form of the same graph S1, S2, S3 with same parameter like time versus temperature. And these red peaks actually define at which particular temperature actually the hydrocarbon generated. And you observe these peaks and that particular software that is attached with that equipment help to pick these peaks and to record the data of S1, S2, S3 in these units. And then after acquiring these data in particular units, we convert these data into another parameter like hydrogen index, oxygen index, and production index. And particularly this TOC can also be measured with this equipment, and also some separate equipment are also available to measure only total organic carbon in your particular sample. So here you can clarify yourself that these S1, S2, S3, whatever their units are, you put these in another equation for hydrogen index and oxygen index and calculate these indices. And these indices also can be plotted on a graph and they can help you to identify different type of kerogen in your particular sample. Similarly, if you use temperature as well, even these are actually the kerogen temperature. These are not borehole temperature, so you should separate these. These are temperatures that that your sample was exposed to. So, onset of oil generation at around 445 degrees centigrade, type 1 kerogen generate oil. Similarly, at 435 type 2 kerogen generate oil, and at this rate type 3 kerogen generate oil. And indirectly, with the help of these temperature ranges and the observed oil generation or oil sample, you can decide which type of kerogen exists in your particular sample. And as you can observe, the gas generation will happen at around 460 centigrade, this pyrolysis temperature. You can also say it is a pyrolysis temperature. Okay, here is the data plot. I will only highlight here the S2. Here you can say S2 curve. Here are different its interpretation. If S2 values fall somewhere here, here are its, you can say, range from point 1 to 100. And if it's fall here, you can say it's a poor, then fair, then good, then very good, and here are its thresholds. And even based on S2, you can differentiate your quality of organic matter as well. Similarly, hydrogen index helps you to differentiate between gas and oil. Either your kerosene will produce gas or oil. If those peaks are only fall somewhere here, you can say it will only generate gas. If it go beyond that, it can produce both gas and oil. And here are the different ranges of hydrogen index. And this hydrogen index was calculated based on S1, S2, S3 values. You can check the formula in previous slide. So this is an example of plot of data that actually you acquired from pyrolysis analysis. Okay, after pyrolysis, there is also another technique that is also called biological paleothermometers. Those also help you to assess the maturity of your kerogen. Okay, first of all, vitrinite. Vitrinite is a polyorganic material derived from the connective tissues of vascular plants. Okay, the microorganism, you can say, the material. And the reflectance of vitrinite, this particular substance, if exists in your kerogen or in your sample, the reflectance of vitrinite changes with heat. As you increase the heat, its reflectance will change, and that reflectance actually then calibrated or attached to some numbers, and those numbers actually help to identify the maturity of your kerogen. The most commonly used thermal indicator is the benchmark for the maturation study in the petroleum and coal industry. This technique is primarily used for Devonian and younger classic sediments and coals. Also, some prediction on it for which type of sediment these are more useful. For further detail, you can visit this site. You can read the more detail. But the basic idea is about it is actually the reflectance of a particular, you can say, material that is deposited with your organic matter. Okay, yeah, it will help you to explain these this kerogen sample in a microscope. This is a, a whole image is of your kerogen sample. You can say it may be within the source rock, and we just focus on the kerogen, and we are going to decide which type of kerogen actually exists in your particular sample. Some type or sometime all types of kerogen exist, maybe sometime only one type of kerogen exists in your sample. Similarly, here as you can observe, based on this vitrinite, and this is the vitrinite material, and we noted down its reflectance, and it actually help you to assess which type, and it fall in type 3. Similarly, the other types, inertinite and liptinite, as you can see in this second row, inertinite and here is the liptinite. Those are actually fall in type 1 or type 2 and type 4. So you have to play with these uh, parameters and quantify these parameters, which type of, you can say, material dominant in your sample, whether it's vitrinite dominant or other types are dominant, and then you interpret that which type of kerogen dominant in your sample. Sometimes one type is more dominant than other, and at the end, after some additional tests, you will decide actually which type dominant in your sample and what you expect regarding oil and gas generation from your sample. Okay, these are microscopic views for vitrinite reflectance. Okay, here is a plot, depth versus vitrinite reflectance. If you collected a sample at different depth intervals of particular formation, you can plot these samples with depth, and based on this vitrinite reflectance data only, you can define the maturity of your sample, either it is in mature oil window or immature oil window, or either it is post mature. So it will depends on range of your vitrinite reactants. As you can see, from 0 to 1 it varies for mature oil window. Similarly, for gas window, there is also a little different ranges, and details are given in relevant reference. You can look into those. So if you only have veterinary reactants, still you have ability to define the maturity of your kerogen sample. But the recommendation is you should have multiple data set, and you have to confirm from multiple experiments that either your kerogen is mature or mature, and the results of all the experiments should support each other. Then you can reach to some final conclusion. If they are contradicting, then you have to repeat the experiments. You have to verify whether your source of mature or immature. Okay, next biological paleothermometers are the pollen and spores. These are the organic walled microfossils, most commonly used for gauging paleotemperature. Fossil color, which changes with heating, is used to estimate thermal alteration index. It is also called TAI. And let us these actually help us to examine in situ fossils rather than evaluate and aggregate, just like Kerogen we are going to evaluate. But what are the in situ fossils there? This technique helps to evaluate those. And let's see here. Here are the example of different types of pollen or spores, and the relevant details are also given. Also, this is more relevant to biological sense, and also more relevant to petroleum geochemists who actually work on the source of maturity analysis. But at this level, you should have some basic idea about these pollen and spores, how their color vary, how we allot a specific index to a particular pollen spore, and then decide either our kerogen is mature or immature. Okay, you can look into details about these pollen spores, but we will go to the actual application of these pollen spores. Okay, let's see here. If you observe this column in the middle, Spore coloration means the color of spore or pollen will help you to draw these threshold lines. And these are different index, and based on those index you can define their paleontology. In what paleontology your particular sample fall, and based on that paleontology you can define the kerogen type. And then after that you can also decide whether it is oil prone or gas prone. Similarly, if more fall in black, then it is gas prone. If it is more fall in this coarser algo, it may be going towards oil prone. And based on this spore coloration data, in addition to this vitrinatural reactance, you can define different interval regarding oil prone or gas prone, mean where oil will be generated from source rock and where gas will be generated from source rock. And this information is also very helpful. You just have to plot that data and to decide different types of kerosene. Similarly, at the bottom right corner, you can observe the different windows like oil window, condensate, and then dry gas window based on this vitrinitural reflectance data as well. And threshold values are here. You can specify the limits or range of R naught to decide that either it will generate oil or either it will generate gas. The one important point, your kerosene will only generate oil and gas if it is mature. If it is immature, as you see here in blank at the bottom right corner, uh, even all your data set will also support that all the point from where it is coming, either coming from a particular depth, actually they help us to interpret that these particular rocks or source rocks or kerogen, whatever you have here, those are immature. And as you move forward, and these points actually represent that your source rock now have entered into mature form because it's going to generate oil and gas. And even on based on this data, there is no data point for condensate dry gas. Means this type of source rock will only generate oil. So you have to play with the data to decide what type of hydrocarbon you will get from your source rock. Similarly, let's see here from surface to depth. Here are different parameters. It is the summary of different parameters. First of temperature, and then vitrinite reluctance, and spore coloration, and based on those different colors, you can define the different windows, oil window or gas window. Okay, here is some more detail regarding the spore color index, how we allot different values to that particular index. As you can see, generalized correlation of different maturity indices, and here are its ranges. As you can observe, if it's high, if it's around 4, it will mature, or if it will increase and reach up to 8 or up to 9, then you can expect okay, there is a chance of oil and gas generation from that particular source rock. Similarly, in parallel, other parameters are also important like veterinary reluctance, what's range for that, and the temperature. Actually, these are key parameters that mostly people believe and mostly people use in the industry as well to decide about the maturity of your source rock. Okay, final point that is important to know, geochemists use a wide variety of organic compounds derived from both terrestrial and marine organisms to determine deposition environments and thermal maturity. These analyses include elemental analysis, also called gas chromatography, and other are Fourier transform, infrared spectroscopy, and some other analysis like biomarkers, spectral fluorescence, and rock evil pyrolysis. And today we discuss detail about rock evil pyrolysis. So similarly, other details for others you can go through your book or some additional literature to look into those details. But at this stage and for bachelor level understanding of the source of valuation, I feel this is an enough material to get some initial idea about this process that is actually involved in source rock evaluation. If you still have some question, you can email me, you can message me in your WhatsApp group. I even you can call me and we can discuss about different concepts. If you have any confusion in understanding these concepts, let's talk to me and I will try my best to explain you in detail. Okay, that is the end of source rock evaluation and let's go through it. Thank you and bye.